Hey everybody, welcome back to another chemistry video lesson. Today we're going to take a look at chemical kinetics. Chemical kinetics deals with how quickly reactions take place. So far we've been spending a lot of time on how much is formed, how much product is formed, how much reactant is needed to make that product, but now we're going to turn our attentions to what's known as the kinetics of the reaction, or how quickly the reaction takes place. Now you know that if you have food at home that you're going to keep it in the refrigerator to keep it from spoiling. Well, the reason we do that is we want to slow down that rate of reaction. So understanding how quickly reactions take place can have a huge impact on how we use them. Another example would be with medication. A lot of times medication tells you to take it every 2 to 4 hours, every 6 to 8 hours. How do they know all that stuff? Well, it's because they know how quickly it takes for that chemical to take effect and do its thing. So we're going to look at how they can figure that out and where that comes from. Okay, so first of all, kinetics is the study of how fast the reactions occur. The basic premise or the theory behind all of this is something called the collision theory. Now, the collision theory is not that complicated. It's really just built around the idea that in order for these two particles here to react, they must first collide together. That's your first step. If they don't collide together, there's no way for these two particles to react together. So the chemical components have to come together in order for that to happen. So whenever you're answering questions about chemical kinetics, when it says, why does the reaction do this? Why does the reaction do that? Why is it speeding it up? You want to mention something about the collisions increasing. And there's a number of ways that we can get these collisions to increase. Okay, but before we get to that though, we need to look at one other thing, because it's not just that they collide together, because here's the thing, these particles are colliding all the time, but the reaction doesn't always take place. So let's see what the second factor is besides the collision. The second thing that we need in order for a reaction to occur is that when the particles collide together, that when they smash together, they have to have enough energy that they can break the bonds. Remember, we talked about bonds, atoms are held together in bonds. Well, in order to get the reaction to occur, you have to break those bonds first, then reform bonds afterwards. So in order to do that, we have to hit what's called an activation energy. So this is essentially the energy that's holding those particles together. So when the collision happens, it has to happen with enough energy to overcome activation. Okay, what we're looking at down here is something called an energy profile diagram. And what it does is it shows how potential energy and the reaction pathway are related to each other. Reaction pathway just simply says that we're going from reactants to products, and where are we in that particular process. Either we're on the reactant side or we're on the product side. The potential energy, don't worry too much about potential. It's the energy stored in the reaction, but we're just focusing on energy at this point. So the reactants have a certain amount of energy because there's a certain amount of heat in them and they're moving around. Well, when they collide together, if the impact can have enough energy when two particles collide together, that they have enough energy that's 400 kilojoules or higher for this particular reaction, it will then produce products. Okay, and as a result of that, the products will then form and the reaction occurs. If it doesn't, the particles just bounce off of each other and nothing happens and they go back into the reactant stage. So this is the threshold. This is that activation energy that's required in order for the reaction to occur. So in order for reactions to happen, we have to hit this energy or higher. It's called the activated complex. I'm not going to worry about having you guys know the name for that. I'm more concerned that you know that this point here at the very top is the tipping point. So the collision has to occur to break those bonds that are holding the particles together so that they can form new particles and new molecules and new substances, i.e. the products. Okay, now notice that there's a discrepancy here. The energy here, the reactants now have more energy than they did before, right? So the products have higher energy state than the reactants do. Well, hopefully you remember what that means. If the reactants have less energy than the products do, the system, in the case the chemical reaction, had to absorb energy. So when we absorb energy, this would be considered an endothermic process. So part C, or point C here, this energy here from 100 to the 300 is the amount of energy that the reactants had to absorb in order to become products. So this is an endothermic process because we have more energy in the products than we do reactants. The little picture over here just kind of is a visual to kind of give you an idea of what this represents, right? If you're trying to get this rock over the hill, you got to push it up and over the hill to get it down here. So the difference in energy from A to B would be that the rock had more energy, now it has less energy. So this actually would be an exothermic process because the rock will release energy as it rolls down the hill to get lower than it was before. But the idea is that you can't get this rock over to B until you overcome the hill. So the hill represents the activation energy that we have in the chemical reaction. Okay, so to recap, for reactions to occur, the molecules or particles must first collide together. Okay, so they have to collide. And that collision has to have enough kinetic energy, Ke is kinetic energy, equal to or greater than activation energy, Ea, energy of activation. Okay, so that's the two criteria for a reaction to occur. Collision and enough energy so that they can smash together and react. And here's two ways you're going to see these energy profile diagrams. One is that you're going to have reactants are higher than your products. In this case, since there's less energy in the products, where did that energy go? Well, it's the energy that's released. This would be considered an exothermic reaction. Activation energy is always from the reactants to the top of the hill. On the opposite side here, you're going to see an endothermic process. This is where the reactants are lower in energy than the products, and therefore it will have a higher activation energy, and then the products are higher. And this is the energy. The difference between these two levels is the energy that will be absorbed. Okay? All right, so now we know the two criteria that we need for a reaction to occur. So how do reactions make the collisions go up, and how do we make the kinetic energy greater? Okay, so the four factors that affect the reaction rate, one is going to be temperature, so we can increase the rate of collisions, and we can increase the kinetic energy, concentration, catalyst, and surface area of the reactants. So we're going to look at each one of these individually. Okay, so let's take a look at our first effect, which is a temperature effect. And temperature has the biggest impact on all of this. So whenever we want to make a reaction go fastest, temperature is usually the best. But you got to be careful because sometimes making the temperature too high can have other consequences. So if we want to increase the temperature, what it first is it obviously can increase the rate of reaction. So this diagram here is showing us the relative number of particles. What this means is that if this were all of the particles that were available, this is just showing us how many have a particular amount of kinetic energy. So remember, temperature measures the average kinetic energy. So that would be what is going on right here. So at this point on the graph is our average kinetic energy. That's what we got going on here. So our kinetic energy average would be here. Well, the problem with that is that if this is the average kinetic energy, the activation energy has to be here, right? So the average energy of the particles that are reacting don't have enough energy to form the products. Now, if we look at the graph, what this shows us is that as we get higher in kinetic energy, less and less particles have that kinetic energy. So as we get higher and higher, some of them do. So this region right here shows us how many particles actually do have enough kinetic energy for the reaction to happen. So a small little marginal amount of those particles will react and form products. Most of them won't. Okay, that's the idea. If we go the other direction, they get smaller and smaller and smaller, kind of like our grades. The average grade is a C. Some students have A's, some students have F's, but majority of the students are in the C range. Okay, now watch what happens when I increase temperature. When I increase the temperature, my average is now here, right? So I've increased the temperature, so my kinetic energy average is really, really close now to the activation energy. Still might not be at the activation energy, but look at what happens as a result of this. We get way more particles that can now react and form products. So as we increase temperature, we're increasing the amount of particles that have enough kinetic energy to form products. We're increasing the amount of particles that have enough energy to overcome the activation energy. So when we look at temperature, temperature actually has two things that it does. One, if we increase the kinetic energy, the particles are going to move faster, so therefore the collisions will increase. And this is the only one that has really an and, is that it increases the number of collisions with enough energy to overcome Ea, which is, remember, that activation energy. Okay, so the increased temperature will increase the kinetic energy of the reacting particles, higher temperature, more frequency, and increasing the number of collisions. So again, temperature has two effects there. So let's go ahead and take a look at the next one, which is concentration effects. A really simple, very simple idea. If we have few particles in there, we're not going to get as many collisions as we would if there's more particles. So if they're all jammed in there and the concentration goes up, we can get the particles to react more often. Now think about ways that we can increase concentration. We can make the volume smaller, we can add more reactants. If it's a gas, we can increase the pressure. So there's a lot of ways that we can get those particles to come closer together. So when you're answering this question, you want to look at, again, frequency of collisions going up, right? So that's what we just said in those last two. All right. take a look at the third one. Third one is what's called catalyst effects. And you guys hopefully know catalysts speed up reactions, but what a lot of people don't realize is that they do it without being consumed in the reaction. So if you put your catalyst in, you will get your catalyst out. So how a catalyst does this is very different than the other two. It's not going to increase the frequency of collision. So this is the only one that doesn't necessarily make the number of collisions go up. It actually does something a little bit trickier. So this is the energy profile diagram. Or this was our activation energy that we had to overcome to get to the product side. Well, what a catalyst does is it actually changes the way the reaction works. So instead of the reaction going in this direction and having to whatever it normally does, it provides a new pathway, a new way for the reactants to get to products. So it makes a new pathway with a lower activation energy. So if you think about that kid pushing that rock up the hill, well, instead of pushing the rock up the hill, what if the kid dug a hole through the hill and then pushed the rock through the hill? That's the idea. There's a new path. So at that point, the rock could either go up or it could go through the tunnel. Well, it makes sense that if it goes through the tunnel, it'd be a lot easier to do. But it might be hard to dig that tunnel. But that's okay. That's just our analogy. So the point is, lower activation energy with a new pathway is what's going on with the catalyst. Doesn't increase the frequency of collisions, doesn't increase temperature. It simply changes the activation energy, which is very different. Okay, last one is something known as surface area. So if these are my two reactants, right? This is one reactant and the green spheres that are around it are the other reactants. Well, the reactant can only come in contact with the surface of the other reactant, right? The yellow one. So they can only collide on the walls of this material. Nothing in the center can be touched. So that's not good. We can speed this up. We can make this go a little bit faster. What if I were to break this into pieces? If I break it into pieces, the surface area is going to start going up. So you can see that I can increase the surface area. That's what the surface area is, by the way. It's the outside surface area. Okay, anyway. So as the particles get smaller and smaller and smaller, we can then increase the amount of space that these particles can collide. Now we can start hitting those inner particles and speed up the reaction. So what it does is it will expose more particles to react, therefore increasing the frequency of the collisions. And there you have it. That's how you can speed up chemical reactions. The key component here to most of this is finding a way to increase those collisions. Remember, temperature does something adds a little bonus to it. It also makes the collisions go have more energy when they impact. And then don't forget the catalyst. Don't change the frequency of collisions, and then it doesn't change the rate of the kinetic energy of the collision. What it does is provides that new pathway. All right, I will see you guys later. Thanks a lot.